Everybody open up page 145 in your books. What we're going to be doing today is working a lot on dividing whole numbers and decimals. We're going to be estimating our quotients. We're going to develop an algorithm. Then the next class period, we'll use that standard algorithm and then write some fractions. Today, our big focus is going to be on how we do actual division. We're going to give you guys a couple different methods to look at. But it's going to start with fact families. So this is it should be a quick one, because either you understand what fact families are and you can write this in about 10 seconds, or you don't, and then you'll just pick that up once we go over it. But do your best, write the fact families for each of those three problems. Go. Our first fact family. Who can give me all three of them? Anybody? Jet? All three. 9 times 8 is 72. Good. 9 times 8 is 72. What else? 8 times 9 is 72. And? Perfect. Well done. So it's basically just saying, using those three numbers, what are the 4 ways we can put them together? They gave us our first one to start us. So given that, how would I do number 2? Sophia?
I got 6 divided by 8 plus 14.
Ooh. We don't have a commutative property in division.
So do the multiplying?
You can do the multiplying.
Okay, then 6 times 80, or 6 times 18 equals 84.
6 times 14.
14, yes.
Okay.
And then 14 times 6 is 84.
Good. But we don't have a commutative property on the division, but what I can do is change the divisor and the quotient. So I do 84 divided by 14 is 6. And then our last one, Raina? Okay, any questions on any of those? Having those fact families together is going to help you a lot for today's lesson. So understanding that concept, once I know one, I actually know them all. So go ahead and pull out your highlighters. Just a few things to highlight here. The first one, quotients. So when I find the answer to a division problem, I have multiple answers. I could either have a whole number, I can do a decimal, or I can do a fraction. By and large, the rule is do the answer as it was given to you. So if I give you decimals, give my answer in decimals. If I give you fractions, give my answer in fractions. If it's a whole number, you don't even have to think about that because it's basically just going to end. And remember, multiplication and division are what we call inverse operations. Another way to say that is they undo each other. So they're basically opposites. If you can start with those two facts for today, it should make everything else that we're going to do really easy. Again, some math terminology. If I am looking at some numbers and I'm doing a division problem, the number inside of the bar is what we call the dividend. The number on the outside is the divisor, or how many groups I'm breaking it into. Your answer is the quotient. Because division and multiplication are inverse operations, I can rewrite those using multiplication, saying if I do the quotient times the divisor, I get the dividend. And I'm actually going to add one to this. So we can also look at this as a fraction, which would be the dividend is on top, because he's the winner. The divisor is on the bottom. He's the loser that ends up on the outside. And that's going to equal the quotient. Remember, quotient is basically just the answer to a division problem. Damn, don't do that, dude. That's not good. So Austin, you should have that written down in your book. If I put it on the board, you should put it in there. Now we're going to do a couple examples. We're going to look through some thinking. The first one, John knows that 6 times 8 is 48. So 48 divided by 6 is 8. What strategy did he use to evaluate that expression? Linda? No? Good guess, though. I like that one. Austin? Inverse operations, or we could also say, what did we just do in our warm-up? Fact families. So he used inverse operations. Or fact families. So you understood the opposite of multiplication is division, or he just looked at the fact families and said, well, I know 6 times 8 is 48. One way I can rewrite that, 48 divided by 6 is 8. So identify the dividend, divisor, and quotient in the statement 48 divided by 6 is 8. So what is my dividend? Which number is the dividend? Tina? No, not the 6. That? Not the 8. Linda, we got one left. There we go. Dividend. Dividend is the number being divided. So the number being divided is the 48. The divisor is what? Go ahead, Melinda. It's 6 because it's the number of groups it's being divided into. So the divisor is 6, meaning that our quotient is 8. The easy way to think about it again is quotient is the answer to a division problem, meaning that's going to be the part that it's equal to, right?
It's the only thing different. It's the only thing that has a different.
It is also the only one with a different letter. Okay, which values in the statement 48 divided by 6 equals 8 can you switch and the statement is still true? Thought you raised your hand, Mihana. Okay, Sophia, what do you think?
You can switch the divisor and dividend because the quotient's answer.
Quotient's the answer.
So the answer will stay the same, but the 48 and the 6 you can switch them.
Can I?
It'll still be 8.
6 divided by 48?
No, if it was multiplication, yes, but no.
So which ones can I do in the division statement? Which ones can I switch? You do? Because we just did fact families. And?
No. What? I don't know what I'm doing.
That's okay. Billy? So I can switch the 6 and the 8, right? I can switch the divisor and the quotient. So I can do 48 divided by 8 equals 6. Why can I do that? What did we do in our opening, guys? Billy? Fact families. So fact families is a really good reason for why I can do that. Now, why couldn't I do like Sophia originally tried to do and just switch the 6 and the 48? Jet? Goes into decimals or fractions because we don't have a commutative property of division, right? Had it been written initially as a multiplication fact, then I could. Commutative property says I can switch those, no problem. But we can't do that in division. Austin, that's 2. Don't do it. Is John's strategy reasonable for evaluating any division expression? Is John's reasoning reasonable for any division expression? So you guys can look at it. He knows 6 times 8 is 48. 48 divided by 6 is 8. Will that work for anything? Yes, fact families are always true, guys. That's why they are fact families. Okay? Because they are facts. Fact families are always true. Once I have the fact family established, I can rearrange it any way I want to. If it's on the board, you should have it in your module. You have an awfully blank page for everything I got written up there. So is this starting to make sense? You see how these come together? Okay, for you guys, it's on the same page. For me, it's the next one. Initially, when I saw this, I was like, oh man, do I really want to do this? But I do understand a lot of you guys have been learning math this way with some of the new math. So we're going to go through it. I'll be honest, this isn't my favorite, but it does make sense if you think about it. How many of you guys are familiar with, I keep forgetting the term. I want to say it is partial products. There we go. Partial products. It's a way for doing multiplication that they're teaching nowadays and division. So this is basically this estimation strategy that they're covering right here is basically just partial products. And all they're saying is if I look at the division and just use estimation, I can start pulling pieces out that are going to get me closer to the answer. So they basically just start, and Lori said, I first estimated how many sixes are in 34,098. So she started with the fact of saying, okay, 6 times 5,000 is about 30,000. That's pretty close, right? So then she used her estimate, said it's about 5,000. She put that here. And then she subtracted the 30,000, which left her part of what is left. The part left was 4,098. So then she said, well, I got 4,098. So first I tried 6 times 700. That was 4,200. That was too big. So then I just went down one, and then 6 times 600, which was 3,600. Then I took that away, and I put the 600 up here. That left me with 498. At that point, she's looking at, she's like, okay, I just did 650. That was too small, way too small, 300. So to get closer, she did 6 times 8 was 480. I took that away. She only had 18 left, and knew at that point 6 times 3 was 18. And then all she had to do at that point was add up all of the pieces to figure out how many times 6 went into 34,098. Does that make sense to everybody? Do you understand what she did? Which part did you get, Jaden? You didn't understand that looking at 34,000, 6 would go in about 5,000 times. Kind of? Oh, you didn't understand 6 times 5,000 is 30,000. Oh, you did? Because it should be easy math. Because 6 times 5 is 30, and then I just add the 3 zeros. Again, Jaden, honestly, this is why estimation is good. I don't have to be exact. I can just get close. So was her initial guess 5,683? No, she just went close, starting at the first place size, and then just basically moved across. Okay? So the reason we went through that, some of you may like that, but here's a key question. And in each step, why did Lori subtract after she determined each estimate? Yeah, she subtracted each piece as she went down. She subtracted the 30,000, the 3,600, the 480, the 18. Why did she subtract it?
Because she's taking away part by part, so it gradually gets smaller and smaller. It puts whatever she multiplied by on the top, and when you add it all up, it's what you get. What you get is what you multiply to get the actual answer.
Okay, so I'm going to just rephrase what you said a little bit, because you're actually right on there. All she was doing was getting a closer estimate? In a lot of ways it is. But by taking away the part that she was already estimating away, it just got her to smaller numbers to get closer on the estimate. So it ended up with her getting the exact answer, which is really what partial product estimation is all about. So here are Rob and Morgan. They both got it right, but they shortened the process of Lori's logic. So compare Rob and Morgan's strategies. What are similarities and differences? So there's our question. I want you guys to talk as a table, come up with at least one of each. One similarity, one difference. Okay, what similarities did you guys come up with? Anybody got a similarity between their methods? Yeah? Guys, we're talking, or we're not talking, I am, and we're recording.
So they both like similar staircase effects.
Okay, similar staircase.
And they both have a zero.
Both end with zeros. Which is actually really key, guys. If it ends in a zero, that means that I've gotten to a final answer. Tita. Okay. What differences did you see? Okay.
One of them used the estimation strategy, and one of them used just the long division.
Okay. One was an estimation. One was more exact. Okay, so just a quick note on this one. If I get to the end of a division problem, I can use double lines. Whoa, don't know why I did that. There we go. So we can use double lines at the end of a long division problem when the last difference is zero. In other words, if I get down to the end and I have a zero, I can put double lines underneath it. That tells me I got to the end. So it's just kind of a mathematical shorthand saying, here I got down to the answer. So we've got some good numbers here. Carnegie Middle School conducted a month-long food drive and clothing drive to assist in disaster relief. They collected the following items for distribution: 13,312 cans of food, 9,472 blankets, 19,456 batteries, 26,112 bottles of water. Yes?
Are they talking about themselves?
No, it's probably like for Hurricane Ian. Disaster relief. Are you sure? Okay, if the students want to make 256 disaster relief shipping crates, how many bottles of water will they put into each shipping crate? So you guys, this is on the same page, so you can look back and forth between the two. Analyze each solution. What did Morgan and Dustin do differently? Why is one right, one wrong? So I want you guys to talk about this as a table for a couple minutes. See if you can figure out what happened. Okay, who was able to figure out what did Dustin do incorrectly? Sergio? Good. He didn't line up the place values. Okay? First period, I had a whole bunch of people saying he didn't put a zero, but that didn't explain it. The reason was he didn't line up the place values. Okay? When he did the 1, where should that 1 have been written? Should have been written in the hundreds place. Because 256 goes into 261 once. That was correct. And when he subtracted, he got 5 left. But then because he didn't line up his place values, he didn't realize there should have been a 0 above the tens, because 256 doesn't go into 51. He just brought down both the 1 and the 2. So technically his math was right. 1 goes into 261 once, 5 left over, bring down the 12, it goes twice. He just forgot the 0 in between. So that's why it's so really important, guys. Line up your place values while you're doing your division. If you line up your place values, you should be okay. How could Dustin have checked his work? There's actually 2 answers to this one. Austin? Okay. Inverse operations could have multiplied. What else could he have done? The one we've actually been working on the last few class periods. Could have estimated. And he estimated he would have realized he needed 3 places in his answer instead of just 2. So place value would have helped him. So Dustin should have had 3 digits in his quotient. How could he determine that before he started dividing? Estimating. Remember, the whole purpose on estimating, do the math easy to make sure your answer makes sense, that it's reasonable. Right, Liam? Questions on this page? Okay, let's go to our last page. I'm going to actually teach you guys a third method. We've already done 2 today. We've done the estimation strategy. We've done long division. What we haven't done is shown you an algorithm. This one becomes really important when I have multi-digit divisors. Because I want to do 256 shipping crates, how many of you know the facts family for 256 off the top of your head?
1,
Really?
8, 6, 8 and 6.
No, the multiples of 256. That was actually good. So let me show you guys a really easy way to do this. All we have to do is build what we call a ratio table. So you guys do this really quickly over here. You're going to list the first column from 1 to 9. On the second column, I'm going to use the number of my divisor, in this case, 256. What makes this easy is all we're doing is adding. All of you guys should be able to add 256 to 256 in your head. In your head. Because 6 plus 6 is what? 12. 5 plus 5 is plus 1, because it was a 12. 11 gives me a 1. 2 plus 2 is plus 1 is. Once you have the first 2 written, now I'm just adding those up. So 6 and 2 is 8. 5 and 1 is 6. 2 and 5 is 7. Easy, right? 6 and 8 is 14. 5 and 6 is 11. Plus 1 is 12. 2 and 7 is 9. Plus 1 is 10. 6 and 4 is 10. 5 and 2 is 7. Plus 1 is 8. 2 and 0 is 2. Then a 1. 6 and 0 is 6. 5 and 3 is 18, or 13. 2 and 2 is 4. Plus 1 is 5. 6 and 6 is 12. 5 and 8 is 8. Plus 1 is 9. 2 and 5 is 7. Plus my 1. 6 and 2 is 8. 5 and 9 is 14. 2 and 7 is 10. Plus the 1 is 0. 1 and 1 is 2. 6 and 8 is 14. 9, 10. 2, 3, and then a 2. You now have your first 9 multiples of 256, which should make your actual division quite easy. So we'll give you guys about 3 minutes. Go ahead and do the divisions for the cans of food, the blankets, and the batteries. Okay, who can give me the numbers for the cans of food? What was it? Brandon? Guys. 1, 3, 3, 1, 2. Did I write it correctly? Okay. Guys, here's where this algorithm should help you. 256, we'll go into 1? No. 13? No. 133? No. 1,331? Yes. If I look at my chart, it should make it very easy. That's 5 times. And I've also now have the answer, so that's going to subtract 1,280. Gives me a 1, 5, 512. That's going to go twice. How easy was that? If I've got the chart built, how long did it take us to do that chart? Not long at all, because literally all I'm doing is adding 256 each time, right? But you see how easy it made the problem? What about blankets? What was my number for the blankets? 9472. So I do the same thing. 947, that's going to go 3 times. Subtract 768. Do this math, gives us 9. 13 gives us a 7. 1792, 37. How easy can it be? How can it be easier than that? Seriously. It's like a cheat sheet, guys. I just built a cheat sheet that took me, if I tried really hard, I could probably do that in under 30 seconds because I'm only adding 256. If you build it yourself during the test. Okay, guys, just 2 Matthew workspaces. Have a great night.